We're here at Manchester University's Computer Science Department with Professor Steve Furber. Steve is the ICL Professor of Computer Engineering, but he was also one of the designers of the BBC Micro's hardware and the ARM chip after that, which of course we have in our mobile phones and in the Raspberry Pi, and chaired the Royal Society's Shutdown or Restart report on computing in schools, which I think many see as one of the key documents in the curriculum change that we've seen over the last few years. Steve, thank you ever so much for bringing us down here into the SpiNNaker machine room. So this machine uses a large number of these ARM chips. What is it? What is it going to do?
SpiNNaker is a massively parallel computer designed principally for modelling the brain in real time. Components of the brain. The whole brain is still much too big a job for any modern computer. And the machine you see behind me here is the large SpiNNaker machine that we're going to make openly accessible from March 22nd, 2016. This includes 500,000 ARM processor cores, and each core can model several hundred neurons, up to 1,000 at most. So with this machine we can potentially model up to 500 million neurons, 500 billion synaptic connections between those neurons. And it runs in real time, so we can interface it to robotic systems. To give you an idea of scale, a mouse brain is about 100 million neurons, so one cabinet here is capable of modelling a network of the complexity of a mouse brain. But the human brain is 1,000 times bigger than that, so we're nowhere near the full human brain with this machine.
So wiring one of those cabinets to a little robotic mouse, how would that differ from an actual mouse?
If we had a complete mouse brain and we connected it to a robotic mouse, probably a virtual robotic mouse, because they're very difficult to make in practice, then in principle what we'd expect is to be able to reproduce the behaviour of a real mouse. Now that's a huge challenge.
Yes.
There's a lot we don't know about the details of a mouse brain, and of course on SpiNNaker we're running somewhat simplified models, so our neuron models are simpler than the full detail of the biology. We don't know what the consequences of that simplification will be, but the hope is that with a full 100 million neuron network, you could begin to see some of the relationships between the brain of the mouse and its behaviour.
So we have this big computational thinking idea of abstraction, where we put to one side some of the complexity of the problem. What have you done with that simplification from how a neuron works to how you're modelling neurons in SpiNNaker?
The kind of abstraction we're implementing in SpiNNaker is we're abstracting away most of the physical structure of the neuron in the brain, most of the physical details, and we're using what are called point neuron models. So we treat the neuron as existing at a single point in space, and all the inputs come into that point, and then the output goes out to other neurons. So it's quite a well-accepted abstraction, but of course it is losing aspects of biological realism. Now some of those we can put back in. Because our neuron model is programmed in software, it's very flexible. We don't have the right sort of compute engine to implement the fully detailed biological models of the sort that Henry Markram likes to use at the Blue Brain Project. We are the wrong computer for those very detailed models, but we can add in key bits of detail. So for example, if you wish to have a model that represented the different branches of the dendritic tree where the inputs connect, you can do that on SpiNNaker. The current model don't do that, but that's a possible extension of what we do.
So what can you do with SpiNNaker that you couldn't do with a more traditional sort of computer architecture?
SpiNNaker's great advantage over conventional computers, even high-end, very expensive supercomputers, is in the way we implement communication. neurons are highly connected and they communicate just by sending very simple messages. They basically go ping to each other every so often. And there's no information in the size or shape of the ping, it's merely its timing. And so effectively, every time a neuron goes ping in this machine, we're sending about one bit of information around. Now a conventional machine has a communication system that's optimized for sending quite large packets, kilobytes of data. But sending a single bit in a kilobyte packet is very inefficient. So in SpiNNaker we've made the communications extremely lightweight and flexible. So we send one bit in a 40-bit packet.
That's great, thank you very much. I think many teachers struggle to understand how computers work at the hardware layer and perhaps struggle even more to explain those ideas to their students. What model should a 14-year-old have of how a computer actually works, and what's the best way for a teacher to explain that?
I think it's useful for everybody to have a very basic understanding of the standard computer model, which is the idea that you have a memory and you have an engine that processes the memory and you have a connection between the two of them. And I think some feeling for the level at which the engine, the central processor unit, operates is also useful. What does an instruction do at the machine level? Because most of the time you program computers in a high-level language where you have quite abstract concepts which we know the computer grinds down into basic instructions. So to know that an instruction does something such as read a memory location and transfer the value to a register and then add two registers together and then store the register back, I think everybody should have at least a sort of conceptual understanding that that's what the machine is doing at its core. Several times a year I give a school's lecture which is aimed at sixth formers on computers and brains. And what I try and do there is in fact describe the computer at that level and describe the brain at the level of a neural network and try and contrast, find the similarities but also the differences between the two information processing systems.
So thinking about SpiNNaker, does the way we think about algorithms or the way we think about programming have to change when we're working with that sort of massively parallel architecture?
We have this event-driven model, which means that we write programs in a slightly different style, but we use standard languages and the coding is standard. But I think for most SpiNNaker users, they don't want to think about the machine at that level at all. They want to think about the machine as basically a large graph-solving engine. The graph may be a neural network, or it may be a Bayesian network, or it may be some more abstract network representation of a problem. But you really want to think about your problem as a very large network of relatively simple processes that interact by passing simple messages to each other. And if you can conceive of your program in that way, then SpiNNaker can probably support it quite effectively.
Okay. Can you give me an example of something where event-driven programming would be an easy approach to take?
Event-driven programming is the standard model for a lot of real-time systems. Okay. So if you look at the engine management system in your car, it has very strict real-time constraints. It has to know the exact position of the crankshaft, know when all the pistons are coming to the appropriate point to emit a spark, and then it has to look up a table. So it will receive information about the state of the engine as events, and then it will have to time itself very carefully to produce the spark at the right time for that particular cylinder. So a lot of real-time systems are characteristically event-driven at that level. And this is perhaps a somewhat alien model for many conventional programmers who sit at a desktop writing out a long algorithm. On the other hand, if what you're doing on the desktop is writing a computer game, again you've got to bear real time in mind. Yeah. You have to generate frames on the screen at a rate that's required to make the scene progress realistically. And so there you've got to understand real-time constraints as well.
If SpiNNaker, or perhaps SpiNNaker's successor, manages to replicate, to emulate the structure of a brain, do you think a mind will emerge? Will the machine be able to think? Will it become conscious?
These are very deep questions of a philosophical nature to which we don't currently know the answer. I think the majority of neuroscientists that I talk to would say yes. If you build a structure that's functionally equivalent to the brain, then you'd expect those characteristics to emerge. But of course, this is controversial. And for example, Roger Penrose, in his book The Emperor's New Mind, argues that this kind of model will never be sufficient to display consciousness, and that you need something above and beyond the kind of Newtonian physics that we're modelling here. He suggests that something beyond maybe quantum effects in the neurons. I don't know many neuroscientists who accept his argument, but there is at least room for debate. And the way we'll find out is by building these systems and seeing what happens.
Do you have a view? What do you expect will happen?
My view is that the Newtonian model seems to explain a surprising number of phenomena which look complex, but when you build the right model, they kind of happen automatically as a result of the physics of the model. And that seems to work very well for simpler things. So there are very nice, simple models of how an insect walks. Insect motion looks complicated, but actually the explanation is quite simple. And my instinct is that will probably continue to be true. But of course, consciousness is such a subjective phenomenon and such a mystery that to extend insect walking to consciousness is an unreasonably large leap for our current state of knowledge.
For my generation, the BBC Micro had a huge impact on our appreciation of computing. Personally, I used them in school. I did have my O-level in computer studies done on BBC Micros. I had one of these at home. How could we best take that legacy forward? What should we be doing around that sort of computing platform in schools these days?
Well, I think the changes in curriculum that have been coming through since 2014 are an important step in the right direction. I think we need to encourage pupils at school to feel that they can be not only users of technology but also creators. I mean, that was almost the mission statement for the Royal Society report. That we need to feel we own the technology and we can influence it and we can create better technology. So I'd really like to see that movement continue and evolve. Perhaps for the future, an important way to take it would be to encourage pupils to think about programming multi-core devices, because computers in the future are going to be similar to SpiNNaker. They're going to have many, many processors. And that's a new way of thinking for all programmers. And I think the best encouragement is to start them early thinking about that problem.
And simple programming languages like Scratch have that sort of event-driven model. They're available if teachers introduce those ideas and approach programming in that sort of paradigm.
Yes, of course, Scratch is a very good tool for introducing pupils very early to programming concepts without even realizing you're programming. Yes. I think that's great, yes. And with the kind of work we're doing with SpiNNaker, with neural networks, I think they're going to be increasingly important. Industries getting very excited about deep networks. And it would be really encouraging to find some ways to get school children involved in SpiNNaker, perhaps programming the machine from the classroom.
Finally, talking about the Royal Society's report, which you chaired, I think most of us are pretty glad that the decisions shut down or restart came down in favour of restart. But over the last 4 years, what surprised you about the way computing in school has moved on following your recommendations there?
Well, I must admit I'm always somewhat surprised when that kind of report by the Royal Society does actually appear to carry influence, and change did happen as a result. I was very pleased, of course, and to be balanced, it wasn't simply the Royal Society report that instigated the change. At very much the same time there was the Livingston Hope report that was sponsored by Nesta, and possibly even more influential was the McTaggart lecture by Eric Schmidt, the chief of Google, who was also quite critical of the state of computing in British schools. I think these three things together were sufficient to persuade the government that change was necessary. I was quite encouraged that once the change got underway, that the Royal Society report was probably seen as the most authoritative reference to guide the way the change went. So that really felt like the time we'd spent on the report was well spent. Yes, I'm always surprised when things I have a role in carry some influence. Am I supposed to say that?
But the things that you've done have had such huge impact on what's happened with computing education in school. You know, thinking back to the BBC Micro days and what's happened since then. So, yeah.
Well, yes, but a lot of it's serendipity. It's being in the right place at the right time. I mean, I think when we started on the BBC Micro project, I mean, the BBC were confidently telling Acorn that, you know, on the back of this series of programs, they should expect to sell about 12,000 machines. I mean, that was the estimate, and of course, the 12,000 turned out to be 100 times larger, 1.5 million machines. Nobody anticipated the wave of interest that emerged in the early 80s. That the BBC Micro was a part of, but not, again, it wasn't the only machine. Sinclair sold even more machines than Acorn. I like to think the BBC Micro was quite influential in establishing a sort of a quality baseline. And a lot of people I've met since who cut their programming teeth in that era say it was the BBC Micro that was the machine that brought them into programming and influenced the rest of their careers. But as in most of these things, you don't realise this is what you're doing at the time you're doing it. It's just the machine just turned out to have this big influence.
Professor Steve Furber, thank you so much for your time this afternoon. Thank you.
You're very well. Thank you. Thank you very much.
Don't miss out on Computing at School's great content here on YouTube. Subscribe to our CAS TV channel.